Pascal's law states pressure applied on a confined fluid is transmitted undiminished in all directions and acts with equal force on equal areas and at right angles to them. Back in the 17th century, the French scientist Pascal began to define what happens when you use fluid to transmit power. Of course, people have been using fluid power devices like the water wheel for centuries, but his definition, known as Pascal's law, became the foundation for what we now call hydraulics. However, it wasn't until the 1800s that pumps were introduced to effectively deliver high and controlled pressure. In the early 1900s, water was the hydraulic fluid used. For mobile equipment such as earth moving, construction, hauling, and agricultural, cable and winch systems were used. Around 1924, oil hydraulics were introduced for industrial machines. And by the early 1940s, the use of hydraulics in mobile equipment accelerated. By the 1950s, hydraulic pumps and motors had become a common means of power transfer. Hydraulic systems were being developed to produce high power output while staying within minimal space and weight requirements. Early fluid power systems were simple. As hydraulic systems became more complex, the hydraulic filter, which was once non-existent in hydraulic systems, became a critical component. Today, hydraulic systems are designed to be easier to operate and maintain. This places more demands on the filter. You will learn more about how the typical hydraulic filter works in our Filter Types section. Hydraulic systems come in many configurations and can be simple or complex. To understand how the hydraulic system works, let's take a look at a typical hydraulic system. The primary components of a hydraulic system are a power source, a pump, the actuator, the directional control valves, the reservoir, the hydraulic filters, and the hydraulic fluid. Hydraulic systems do not generate power, they transfer energy. Every hydraulic circuit requires a power source, such as an engine or electric motor. In hydraulic terminology, this source is known as a prime mover. Power from the prime mover is introduced into the circuit by the input component, usually a pump. There are three basic types of pumps used on hydraulic equipment: gear or rotary pumps, piston pumps, and vane pumps. Actuators are output components which do the work in the form of linear power, a cylinder, or rotary power, a motor. The directional control valves are flow control valves which regulate the direction of flow and pressure in the hydraulic circuit. The reservoir is a holding tank which functions to store fluid, cool fluid, provide air separation, and provide for easy fluid maintenance. The hydraulic filter's primary function is to clean the hydraulic fluid by removing damaging contaminants. Hydraulic fluids perform four primary functions: transmit power, lubricate moving parts such as pumps, valves, and seals, seal internal components, and cool or dissipate heat. When selecting a hydraulic fluid, follow the manufacturer's recommendations. While hydraulic fluids play a vital role in keeping a hydraulic system operating properly, over 75% of all system failures are a direct result of contamination. Contaminants in hydraulic fluid include particulates, such as dust, dirt, sand, rust, fibers, elastomers, and paint chips, wear metals, water, sealant, such as Teflon tape and paste from repairs, sludge, oxidation, and other corrosion products, acids and other chemicals, and microorganisms in high water-based fluids. Contaminants can enter a hydraulic system in several ways: built in during the manufacturing and assembly process, internally generated during normal operation, and ingested from outside the system during normal operation. Built-in contaminants include dust, welding slag, rubber particles from hoses and seals, sand from castings, and metal debris from machined components. If the hydraulic system is not properly flushed, these contaminants will be left in the system. Also new, Unfiltered hydraulic fluid initially added to the system can be a source of contamination due to cross-contamination and also to the complexity of new additives in the fluids. Pre-filtering of new hydraulic fluid is important to prevent this form of contamination. Internally generated contaminants occur during normal operation as component wear debris and chemical byproducts react with component surfaces to generate more contamination. Hydraulic systems wear in many different ways. Adhesive wear results when moving parts tend to stick together. Abrasive wear is caused when hard particles wear on adjacent surfaces. Fatigue wear is surface failure that results from the reversing of loads. Corrosive wear is the loss of material over a large area, typically caused by water or chemical contamination in the fluid. Cavitation wear, or the formation of partial vacuums within the fluid, is caused by drastic pressure changes. These pressure changes, while microscopic, can cause severe damage to the metal in contact. Erosive wear occurs when fine particles in a high-speed stream of fluid eat away a metering edge or critical surface. Ingested contaminants come from the surrounding environment. Most dirt particulates enter the hydraulic system through vents, breather caps, worn seals, and cylinder rods, and other system openings. Particulates in the 1 to 20 micron range are typically the most damaging to the hydraulic system. Water can also be ingested into your hydraulic system through condensation, seals, and vents. Water in hydraulic fluid can cause chemical corrosion. Water can break down fluid additives and chemistry, destroying the lubricating properties of the fluid. Elevated temperatures and high flow rate can lead to further breakdown of the fluids. Elevated temperatures can speed up the breakdown of the fluid, while the high flow rate can lead to electrostatic discharge, which also accelerates the breakdown of the fluid. Poor preventive maintenance practices are the leading causes of hydraulic system and component failures. Following proper maintenance practices can eliminate most system failures. Along with good maintenance practices, proper filtration is the most effective method for controlling contaminants in your hydraulic system. Baldwin manufactures a wide range of hydraulic filter products to help keep your equipment running efficiently. You will learn more about how to choose the right filter for your application in the Filter Types section. The purpose of the hydraulic filter is to promote long system life by keeping damaging contaminants out of the hydraulic fluid. To better understand how a hydraulic filter works, let's look at the components of a typical spin-on filter. The primary components are a base plate assembly, a bottom end cap, a center tube, the filter media, a top end cap, a compression spring, and the canister. Fluid enters here, is filtered through the media, passes through the center tube, and into the system. Many factors determine the proper hydraulic filter to be installed, including the system's operating pressure, the location where the filter will be used, the type of fluid used, the amount of fluid flow required for system operation, and the fluid cleanliness level, or ISO code, required by the specific application. Hydraulic systems come in many configurations and can be simple or complex in design. Today's heavy-duty hydraulic systems run at higher pressures and faster cycle times than ever before, causing greater system stress and increased sensitivity to contamination. Baldwin provides a wide range of low, medium, and high-pressure hydraulic filters to meet any hydraulic system's configuration. Low-pressure hydraulic filters have working pressure up to 150 psi and burst pressure up to 300 psi. Medium-pressure hydraulic filters have working pressure up to 500 psi and burst pressure up to 1,000 to 1,500 psi. High-pressure hydraulic filters have working pressure up to 3,000 psi and burst pressure up to 6,000 psi. Hydraulic systems are using an increasing number of filters. Increased sophistication and the use of sensitive, closed-tolerance components often require several filters in different locations in the system instead of just one. These filters include suction side filters, pressure side filters, return side filters, and offline filters. Suction side filters, which are located before the hydraulic pump, protect the pump from contaminants in the fluid. Suction side filters may be located in the line between the reservoir and the pump, or may be a wire screen on the end of the pickup line in the reservoir. Some manufacturers do not recommend the use of suction side filters because they can cause cavitation erosion. If using a suction side filter, use a wire screen filter with a higher micron rating. Pressure side filters are located downstream from the hydraulic pump. Pressure side filters clean the fluid as it exits the pump, protecting the more expensive, sensitive components such as valves and actuators from contaminants generated from the pump. Pressure side filters are designed to handle the system pressure. They are also sized for the specific flow rate in the pressure line. Return side filters, which are located between the control valve and the reservoir, are the last components the fluid passes through before returning to the reservoir. Return side filters capture wear debris from the system's working components, as well as contaminants that enter the system through worn cylinder rod seals. Offline filters, or kidney filters, are used on an offline filtration system that is added to the hydraulic system to filter the fluid in the reservoir independently from any other filters in the system. This system includes a separate circulation pump and electric motor that continuously pumps the fluid out of the reservoir, through the filter, and back into the reservoir, providing constant cleanliness levels of the fluid. Also available are intake breathers. Intake breathers are located on the reservoir and prevent contaminants from entering the reservoir while maintaining the reservoir's atmospheric pressure. Breathers prevent moisture and contaminants larger than 3 microns from entering the reservoir. Since most contaminants enter through the reservoir, the use of a breather is a good idea. There are many types of hydraulic fluids used in hydraulic systems, but hydraulic fluids can be broken down into 3 main categories: petroleum-based fluids, fire-resistant fluids, and biodegradable fluids. Petroleum-based fluids are by far the most common fluids used in hydraulic systems today. Petroleum-based fluids have good lubricity and are low in cost and readily available. Most petroleum-based fluids contain additives to help prevent rust, oxidation, foam, and wear. The disadvantages of petroleum-based fluids are low fire resistance, high toxicity, and poor biodegradability. Fire-resistant fluids are used in high fire risk environments, such as steel mills, welding operations, and underground mining, where potential ignition sources such as open flames, sparks, or hot metals exist. Biodegradable fluids are becoming more popular, especially in applications where fluid leakage and spills could have a negative impact on the environment. The most common applications for environmental fluids are agricultural, forestry, mining, and construction machinery, boats and marine equipment, and offshore drilling operations. When selecting a hydraulic fluid, follow the manufacturer's recommendation. The manufacturer has designed the equipment to a certain fluid performance level. Without proper fluid, seals may leak, swell, or prematurely wear out. This can generate heat, causing the fluid to overheat and may allow entry of contaminants into the system. Excessive heat can cause breakdown of the fluid itself. The fluid flow in your system will also be a factor in determining the correct filter use. It is important to have the right size filter to meet your system's requirements. Because fluid can only travel through the filter media so fast, a system with a faster flow rate will need larger filters than a system with a slower flow rate. If the filter is too small, it will not be able to handle the system flow rate and will create excessive pressure drop. This could result in reduced fluid flow on the outlet side of the filter, causing heat to be generated by non-lubricated components. If the filter is too large, it will require more fluid and be more expensive to replace. Particle counting is the most common method for determining a system's fluid cleanliness level. The ISO 4406 code is used by most manufacturers to determine how many particles over the size of 4, 6, and 14 microns are present in a sample of fluid of a known volume, usually 1 milliliter or 100 milliliters. For example, A hydraulic cartridge valve manufacturer may recommend an ISO cleanliness level of 18, 16, 13 for their product. 18 equals the range of number of particles greater than 4 microns. 16 equals the range of number of particles greater than 6 microns. 13 equals the range of number of particles greater than 14 microns. In this example, to meet the manufacturer's specifications, a 1 milliliter sample of fluid should contain no more than 1,300 to 2,500 particles greater than 4 microns in size, 320 to 640 particles greater than 6 microns in size, and 40 to 80 particles greater than 14 microns in size. A hydraulic filter also has performance requirements to ensure the filter meets or exceeds OEM and customer requirements. These requirements include the amount of restriction or resistance to fluid flow caused by the filter, and the amount of contaminant the filter needs to hold to meet service interval expectations. The filter must be able to work with and not against the system. This means it should create the minimum resistance to flow while maintaining the high efficiency required for good protection. The resistance to flow increases as the filter element becomes contaminated. The filter must be able to provide enough dirt holding capacity to meet service interval expectations. When selecting a filter, it is important to note and understand performance ratings. Overall performance is expressed through micron ratings, beta ratios, efficiency, and capacity. A filter's micron rating is the measurement of the size of contaminant that can be efficiently captured by the filter. Filters typically trap contaminants in the 3 to 30 micron range. Though microscopic in size, these contaminants can cause extreme damage to the system. Remember, something as small as a human hair is 50 microns. Beta ratio describes how efficient a filter is in trapping particles of a certain size. A multi-pass test is used to count the number of particles of a given size before and after fluid passes through a filter. This information is converted into the beta ratio using this formula. In this example, at the 10 micron level, the number of particles upstream is 2,000. This number is divided by the number of particles downstream, which is 1,000. So at the 10 micron level, the beta ratio is 2. Efficiency is calculated by taking the beta ratio minus 1 divided by the beta ratio. This number is multiplied times 100. In this example, the efficiency is 50%. This is a nominal efficiency rating. Efficiency is largely determined by the filter media. Media that is more restrictive will filter out more and smaller particles, thus giving the filter higher efficiency. That same restrictive media, however, may lower the filter's capacity. Capacity is the amount of contaminants the filter media can hold before the pores begin to plug, interrupting proper fluid flow through the filter. Highly restrictive media that increases efficiency allows less fluid flow and, as a result, decreases capacity. So, as efficiency increases, capacity typically decreases. Therefore, a filter with high capacity may have less efficiency. Because of this, filters must be capable of removing the damaging particles while still allowing for proper fluid flow. Understanding the correlation between capacity and efficiency is important when selecting the proper filter. A high efficiency rating with low capacity could result in frequent change intervals. On the other hand, high capacity with low efficiency may lead to early system failure because less of the damaging contaminants are captured. Often, a middle ground between efficiency and capacity is the best place to be. When comparing like products from different filter manufacturers, request comparative test results from standardized tests. OEMs have worked with the filter industry to develop a series of symbols depicting industry-accepted test standards for filter comparison. Hydraulic filters themselves have pictograms showing the minimum performance specifications required to meet service interval expectations. These symbols help ensure that the equipment is serviced with a filter product that will provide adequate protection that matches the OEM for the hydraulic application. These symbols will usually reference a test specification developed and/or approved by an industry-recognized association or professional society such as the ISO, International Standards Organization, the NFPA, National Fluid Power Association, or the SAE, Society of Automotive Engineers. All of these organizations work to develop and improve standards for testing fluid power components such as filters and reporting the results. This is important when evaluating the performance ratings of different filter brands. The four major criteria for filter performance are capacity and efficiency, structural integrity, collapse strength, and resistance to flow. Capacity efficiency is determined by the ISO 16889 multi-pass test. This symbol indicates the contaminant holding capacity in grams of the filter under laboratory test conditions, the efficiency or beta ratio in removing the contaminants, and the flow rate at which the filter was tested. In this example, the filter has a holding capacity of 85 grams of a standardized contaminant. The filter's beta ratio is at least 50% efficient in removing particles, which are 10 microns in size or larger. And the fluid flow rate at which the filter was tested is 1.2 liters per second, or equal to about 20 gallons per minute. Structural integrity, or bubble point, is determined by the ISO 2942 test. This test ensures that the filter media does not leak due to holes or improper assembly. The filter element is submerged in a test fluid and slowly pressurized until bubbles appear. In a successful test, bubbles will pass through the filter media at a pressure relative to the efficiency of the filter media. In this example, the filter has a bubble point greater than 0.75 kilopascal. Collapse strength is determined by the ISO 2941 test. This symbol helps ensure reliable operations by defining the minimum acceptable differential pressure at which a structural failure of the filter element will occur. When a filter begins to plug with dirt or during cold starts, the pressure difference between the inlet, the dirty fluid side, is greater than the outlet, the clean fluid side. This can cause the filter to collapse, which in turn causes unfiltered fluid and damaged filter components to be routed back into the system. In this example, the minimum pressure required to collapse the filter is 1,380 kilopascals. Resistance to flow, or maximum differential pressure, shows the maximum allowable differential pressure of a clean filter element tested at a prescribed flow and fluid viscosity. The resistance to flow through the filter is very important. This resistance, or pressure drop, has direct bearing on the filter life. Some hydraulic systems contain a bypass valve. If the filter becomes too restrictive, the bypass valve opens, allowing the fluid to be diverted around the filter. The bypass valve is located in the filter or elsewhere within the hydraulic system. As the length of time the filter spends in bypass increases, so does the contamination level in the system, and the greater the risk of a contamination-related failure. In this example, the initial restriction or differential pressure caused by the filter element must be less than 120 kilopascals when using a fluid with a viscosity of 450 centistokes at a flow rate of 1.2 liters per second. A lot goes into choosing the correct hydraulic filter, and Baldwin provides an extensive line of hydraulic filters which meet performance requirements on all types of operating systems. Spin-on hydraulic filters, such as the Baldwin BT287 series, are typically used on the return side on low-pressure hydraulic systems. With the introduction of the Pure Force hydraulic product line, Baldwin provides a new alternative for medium-pressure hydraulic assemblies. The Pure Force product line consists of filters, bases, and self-housed indicators, which allow users to customize filtration systems to meet their individual needs by allowing users to use a combination of bases, indicators, and a selection of quality hydraulic filters. Cartridge-type filters such as the Baldwin H9000 series with synthetic media are used on applications with high pressure requirements. Choosing the right hydraulic filter for your hydraulic system is essential in helping maximize service life and minimize operating costs. As the sophistication of hydraulic systems and components has increased, so has the importance of system maintenance. Today's hydraulic systems run at high pressures and faster cycle times, causing greater system stress and increased sensitivity to contamination. Contamination can lead to system failure, resulting in major downtime and costly repairs to sensitive components. Adhering to a strict maintenance schedule will help to ensure that your filter is ready to capture damaging contaminants before they reach sensitive system components. In addition to maintaining regular hydraulic filter change intervals, there are several steps you can take to maintain a clean hydraulic system. Flush all systems before the initial startup. On new equipment, changing the hydraulic filter and fluid after the first 50-hour break-in period is recommended. For even better results, change the filter and fluid after 15 hours and again after 50 hours. This allows more time for scrubbing the system. Do not expose the hydraulic system to a dirty environment. Keep the fluid level up in the hydraulic reservoir. When adding clean fluid, make sure the container, funnel, pump, and the area around the reservoir is clean. Do not mix different oil bases. Make sure the hydraulic fluid being added is compatible with the hydraulic fluid currently in the system. Do not allow the fluid to reach extreme temperatures above 190 to 200 degrees Fahrenheit. Use clean caps and plugs when replacing hydraulic hoses. Do not leave the system open. Make sure new hoses are thoroughly cleaned before installing them. Repair hydraulic leaks right away. Repair leaking hydraulic cylinders and other components. Have a fluid analysis performed on your hydraulic fluid every 2 years or whenever you suspect a contamination problem. A fluid analysis is an important part of a maintenance program. A fluid analysis ensures that the fluid meets manufacturer's specifications. It can also verify the composition of the fluid and determine its overall contamination level. A fluid analysis can detect potential problems before catastrophic damage occurs. Drain the hydraulic systems, clean the reservoir, and replace with clean hydraulic fluid every 5 to 6 years or whenever a catastrophic failure has occurred. If the hydraulic fluid has broken down from being too hot, you will notice lacquer deposits on the filter cover plate or elsewhere. Gum and lacquer formations point to the need for more frequent fluid and filter changes. These formations also indicate a need for flushing. Some manufacturers recommend flushing hydraulic systems with regular hydraulic fluid, while others recommend the use of solvents or cleaners. When flushing the hydraulic system, follow the manufacturer's recommendations. Some solvents and cleaners on the market today are not recommended for use in flushing hydraulic systems because they are poor lubricants, resulting in damage to moving parts, especially the pump, and they are difficult to remove completely from the system. Just a trace of some of the commercial chlorinated solvents may be enough to break down the oxidation resistance of even the best hydraulic fluids. In the presence of a small amount of water, some of these solvents will corrode steel and copper, as well as damage seals and gaskets. Also, the hydraulic fluid viscosity could be reduced sufficiently to cause malfunction in pumps or valves. Regardless of what is used for flushing the fluid, it will not thoroughly clean the system if it is not completely drained. Flushing is recommended if the fluid is badly contaminated. It is important to follow the manufacturer's recommendations. Cleanliness is most important in servicing hydraulic systems. It doesn't take much dirt to score valves, seize pumps, plug orifices, and cause expensive repair jobs. A well-maintained hydraulic system can help ensure you achieve the best return on your investment. To ensure normal hydraulic filter service life and prevent fluid leakage or possible internal engine damage, it is important that correct installation procedures are followed. Most spin-on hydraulic filters include pictograms on the filters themselves, showing the proper installation procedures. When servicing, first close the shutoff valve to prevent spillage. Unscrew and remove the old filter, making sure the old gasket is also removed. The use of a filter wrench may be required. Wipe the filter mounting base with a clean cloth to remove any contaminants. Remove the protective shrink wrap from the new filter. Check that all required gaskets are included and inspect the filter for dents. A dent creates a concentrated area of stress, causing fatigue, which can shorten the life of a filter. Filters that are dented prior to or during installation should not be used. Apply a thin film of clean fluid to the filter gasket. Do not use grease. When installing a pure force hydraulic filter, the threads also need to be lubricated before installation. Line up the threads on the filter with the threads on the mounting base carefully to avoid cross-threading. Screw on the new filter until the gasket comes into contact with the base. Follow the instructions of the filter manufacturer for final tightening. The pictogram on the filter will tell how many additional turns from gasket contact the filter requires. If the filter cannot be hand tightened to the proper torque, the use of a filter strap wrench is recommended. Place the wrench near the base plate of the filter to avoid damaging the filter during installation. Using a filter wrench other than a strap wrench is not recommended, as some filter wrenches incorporate metal pins designed to help remove the filter. These pins can dent a new filter, which could cause the filter to leak. A hydraulic filter that is not properly tightened to the manufacturer's recommendations may leak or experience gasket blowout. Open the shutoff valve. Make sure the fluid level is full. Start the engine and check for leaks. Again, inspect the filter for dents. There are many types of systems, new and old, using cartridge filters on the market today. When installing a cartridge filter, some common instructions should be followed. When servicing, first close the shutoff valve to prevent spillage. Clean the outside of the housing before removing the filter to keep contaminants out of the hydraulic system. Unscrew the housing cover retainer nut from the filter head to open the housing. Remove the filter and all old gaskets. Wipe the inside of the filter housing with a clean cloth to remove contaminants. Check the new filter to make sure that all required gaskets and seals are included. Also, inspect the filter for damage. Damaged filters should not be used. Reinstall the filter and all necessary gaskets. Replace the housing cover retainer nut. Open the shutoff valve. Make sure the fluid level is full, and finally, start the engine and check for leaks. Remember, when disposing of used hydraulic filters, follow all environmental regulations in your area.